These lectures aim to introduce the stiffness methods and its application for analyzing the plane frames. Plane frame means we are working on a two-dimensional frames. We are not working on the three-dimensional frames. It is a 2D frames. I hope you have seen the frames. Frames is like members that are connected with others like columns, beams. If you have seen those kind of connected members, that's the frames. We are not working on the connection design between them or anything. It's just totally perfect perfect frame that we are working on. So I think that is just a frame. So today's lectures we will introduce the topics, and then we will do the stiffness methods, analysis methods. Probably this lecture is divided. Probably I will fix up. It is a week number 7. But today's lecture generally divided into these ones. We will not going to complete all the topics. Probably we will work up to the stiffness matrix, and we will solve the half examples on that one. So we will, and the next week again we will continue these lectures on that one. So this topic is divided into 2 weeks because it's a very big topics and the matrix is quite big. So I just give students some times to absorb the concept. All right, so again, this is week 7. I will fix up that one. All right, so that's degree of freedoms. So now you remember that degree of freedoms. Probably I can go back all the way to the week number 2 where we have taken the truss elements. Truss elements, you remember that truss elements. You can put the number 1 for the truss element, and you can use the arrow and label to use arrow to show that this is a near node and this one is a far node. That's we done in the week number 2. And then for that week, if you remember that, we have a 2 degree of freedoms. One is the x displacement degree of freedoms and y displacement degree of freedom, meaning that this point can go in the x direction, can go left and right, or this point can go up and down. Similarly, this point can go left and right, which is x degree of freedom and y degree of freedom. So for these truss elements, we have total 4 degree of freedoms. Like each node has a 2 degree of freedoms. Another node has a 2 degree of freedoms. Everyone okay with that truss, right? If you remember that. Now this is basically truss element. Now we have also take the examples or the beam elements. Again, it has 2 nodes at the end, and it is represented, let's say, element number 1, arrow, also again a same arrow representing this is near node, this one is far node. Now in this sense, we have used the rotation degree of freedoms and the shear degree of freedoms, like a translation degree of freedom. So there is a rotations and vertical translations. So this point has a vertical translations and you have rotations degree of freedoms, right? So that's pretty much you can see vertical translation, rotation, and you have near node and far node. Again, there is a 2 degree of freedoms. Again, there is a 2 degree of freedoms for these ones. Again, there is a 2 degree of freedoms for these points, as you can see. So that was in the previous lectures. I just want you to go back and have a feeling. Because those topics are connected. It's not independent. Now this week's we are doing the frame element. This is, by the way, the beam element. This is beam elements. I hope it is clear so far. Now this week what we are doing? We are doing the frame element. Again, the same concept. It has an element. It has a number 1 as the element number. It would have an arrow to show this is near node and this one is far node. So far so good. That is again this week's topic. I'm talking about frame. Now for the frame, we will have this point can go left and right. This point can go up and down, then this point can rotate. So it has 3 degrees of freedom for this particular point. Again, for these points, you have translations, vertical translation, horizontal translations, and this point can rotate, right? So the frame element can subject to both axial actions like truss element and bending actions like a beam element. So it's basically combination of truss and beams. You can see in these figures that if you are taking those two, they are here. Those tools are here. The rotations are here. So when you are making these truss and beam together, you are basically making the frame. Right? So it is the behavior of the frame is obtained by combining the truss behavior and the beam behaviors, right? So the truss elements have tendency to go like it can pull and you can push. It can stretch or it can do it. It will not have any moments. It cannot bend. That's what I mean. So if you have seen the truss element, the truss elements only can be stretchable or it can be squeezed, but it cannot bend. So that is a truss element. Therefore, there is a degree of freedom for this one. Now for beam element, it can just go up and down the points and those points can rotate. But this point cannot go x and x directions, like it cannot squeeze or squeeze out. So that is a beam elements where the points of the beam elements would have a rotate. It can rotate and it can go up and down. In the truss elements, those points cannot rotate. It can go up and down or it can go left and right. Now, when we this week, when we talk about the frame, again, those same points, they will have, they will can do X and Y. They can do they can do horizontal like squeeze. The element can squeeze and squeeze out and squeeze in. This element can the nodes can go up and down. This node can rotate, meaning that this beam, this element can squeeze in and out and can bend as well. So that's the frame elements, right? All right. Now each node in the frame has a 3 degree of freedoms. As I mentioned, they have 3 degree of freedoms: degree of freedom 1, degree of freedom 2, and degree of freedom 3. Longitudinal displacements and transverse displacement is. So this is longitudinal. Along the length is the longitudinal. That is the fancy way to say the x degree of freedom. So along the length of the element is a longitudinal displacement. Perpendicular to the length is a transverse distance. So this is longitudinal displacement. This is transverse displacement. So I hope you understand that terminology. And the another one is the rotations degree of freedom. That is the rotations degree of freedom. Now, let me ask you questions here, whether you understand or not. Let me check. All right, now testing for your knowledge. So we have, let's say this is a frame elements. Let me make it some at an angle. This one have a node, and let's say this one has a this one has a this degree of freedoms, and this one has a rotations degree of freedoms. This one has this degree of freedoms. This one has this degree of freedoms. This one is this degree of freedom. Now, we want to have a longitudinal displacements, transverse displacements, and rotations. Right. Can you match it up? 1, 3, and 2. Can you please type it up? What is the longitudinal displacements? Is it 1, 2, 3 or transverse displacements? What is that? And rotational, which one is this? Can you please put the numbers in the chat? I hope you understand the questions. I want you to make sure you understand these lines. What is the longitudinal displacements? Which one is transverse displacement? And what is there is a degree of freedoms? Can you please identify? LD equal to which one? TD equal to which one? LD stand for longitudinal displacements. TD stand for transverse displacement, and rotations R stand for rotations. So can you match these numbers 1, 2, and 3? Which one is longitudinal? Which one is rotation? And which one is transverse? 1 is 3, 2, 1. Okay, longitudinal is 1, transverse is 2, rotation is 3. 3, 2, 1, 1 rotation to this ones. Okay, let's do it. Thank you for the answers. Longitudinals along the length. When along, this is the length. This is the element along the length, number 3. Perpendicular to the length. This is the element. Perpendicular to this one is 2. Rotations, the point can rotate, is number 1. Right? So check your answers. Unmute yourself or put in the chats if you don't understand how I get those answers. Thank you for trying and putting the answers. Don't hesitate if you put the wrong answers. Sometimes the wrong answers help you to understand. And if you don't, it is good to make a mistakes right now rather than making mistakes in the exam. So it is a good approach. There is no any issue. But once I explain you, let me know. Oh, there is no question, so let's continue. Now, each frame element has a 6 degree of freedoms. Okay, let me explain you. So each node has a 3 degree of freedoms. Everyone okay with me that you can say that has a longitudinal displacement, transverse displacement, and rotation. So each node has a 3 degree of freedoms. These nodes again has a 3 degree of freedoms. You with me? That has a longitudinal displacements, it has a transverse displacements, and it has a rotational degree of freedoms. So if you take the whole element which has a 2 nodes, you can say that each element has a 6 degree of freedoms. 3 on the left side, 3 on the right side, or 3 on the near node, 3 on the right node. So everyone okay with me that it has a 2 longitudinal degree of freedoms. Here you have 2 longitudinal degree of freedoms. Here you have 2 transverse degree of freedoms, and you have 2 rotational degree of freedoms, right? So that's all sorted at the moment. So 2 longitudinal displacements, 2 transverse displacement, and 2 rotational displacements that you are getting it there. Right. So far so good. Everything I explain you. These ones I already explained you. Displacement, force. Again I explain you these ones. Again these ones. I think this is the modeling. I can explain you the modeling side of it. Okay, that's I will let me explain you the modeling. So when you do the modeling, what you do, you generally put the number 1, 2, 3, 4, and 5. So the circle with the number is representing the node numbering. Node numbers. You with me? So every points that you will get has a node number. Number 1 has a node. Number 2 is a node. Number 3, number 4, number 5. Now someone asked me, does it matter which numbers goes first and which numbers goes at the 2 or which numbers goes at the 3? No, it does not matter. You can put 1 here. You can put 1 here. You can put 3 here. You can put 2 here. You can put 5 here. That is no matters. It's up to you. It is a user defined. But once you put those numbering, you don't need to change it throughout your examples. And in the exams, you no need to worry, or in the assignment questions, you no need to worry to put those node numbering because there is no logic. There is no any engineering thinking required someone's to put 1, 2, 3, 4 node numbering. It is just arbitrary. It is just users. So why we put those numbering? So well, later on when we work on the problems, we will just going to work individual node, individual elements, and then we will assemble them, as you know from the truss and from BIM. So it is useful if we just identify from the start. So I identify from the start. So everyone okay to see the node numbering, right? No questions so far. The green one, node numbering, everyone can do it. Now each node here, you can see each node has a 3 degree of freedoms. This degree of freedom, this degree of freedoms, this degree of freedom. So that you can put the degree of freedoms and you can put those degree of freedoms. Those degree of freedoms, those degree of freedoms, and those degree of freedoms. And numbering, I'm going to explain you how this lowest number, this is matter here. The number 1, 2, 3, 4, 5, 6, that is generally matters here. Which one goes in the which numbering. And finally, we will have arrow to identify which one is near node and which one is far node. So that's the modeling. Modeling generally given to you in the assignment, in the final questions, in the quiz, everywhere the modeling will be given. So you don't need to think about it. So let's do the one modelings with me. Let's say this is a fixed supports. Let's say this is fixed support. Let's say this one is a fixed support. Right. Now, you with me. Number one, number two, number three, number four, number five, and number six. Right? Now, in this case, everyone agree. What I put these ones? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. What does it calls? I just explained you that one before. No need to remember, just exercise to wake you up. What is it? What does it calls? 1, 2, 3, 4, 5, 6. Matters if I put 1 here, if I put 4 here, if I put 6 here, or if I put 1 here. Does it matter? Yes or no? Or it is just arbitrary. You can put it. So far so good. You are understanding. It's not something. It's just I'm talking. Now, these ones here, every node has these arrows. Every node has these arrows. Okay, so far so good. Now, what is this called orange one? You can see every node I put there, it has a two arrows, one going this way, one going up, and another one is the skull. What does it call? Can rotate. This point B has a possibility of going left and right, going up and down, and it can rotate. This point C here, tiny point here, it has possibility going left and right. It has possibility to go up and down, and it can rotate. This point here at E, the small point or node, node has the possibility to go left and right, go up and down, and it can rotate. And these points here that has a possibility of going left and right, going up and down, and it can rotate. And this point has a possibility to go left and right, going up and down, and it can rotate. Right, so that is the meaning of degree of freedoms. Now, one more concept I like to give you that I put the arrow here. That is called location vectors and locations. Oh, sorry. The location vectors representing which one is the near node and which one is the far nodes. Let's keep it consistent here. Right. So this is a location vectors. It is telling me that this is a near node. For this particular element, this is a far node. And I can put number in the square. It is the element number. So element number 1, element number 2, again, it is arbitrary. It does not matter which one you put element number 1, element number 3, element 4, or element 5. It is a random, arbitrary. It does not affect your answer. It is just there to explain the numbering. So this number with the square bracket is called element numbering. 1, 2, 3, 4, 5. There are 5 elements. There are for each 5 elements, we have a 6. We have 6 nodes. Now this location vector is telling me that this is number 1 is near node and far node. This location vector telling me for this element number 2, this is a near node, this is a far node. For this element number 3, we have this one is a near node, this one is a far node. I think it's getting messy, but I hope you understand that this is near node and this one is a far node. So I hope it is clear for you. Now we have total 6 nodes out of 6, there are total 18 degree of freedoms. You can look at that total 18 degree of freedoms. Total degree of freedoms. Total degree of freedoms are 18. You with me? If you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, and if you count them all, there are total 18 degree of freedoms. You are with me? There are total 6 nodes. Each node has a 3 degree of freedoms. So 6 times 3, 18 total degree of freedoms. Now my question is, out of 18, how many free degree of freedoms? And how many fixed degree of freedoms? Right. How many free degree of freedoms and how many fixed degree of freedoms? Because out of 8, if I add them together, I should get 18. So this point here, point A is fixed. So this point cannot go left, right, cannot go up and down, and cannot rotate. So this is fixed. This is fixed. Let's say put fixed, and this one is fixed. You with me? So that is fixed. There are 3 fixed. Now this point A does not support it, so it is free. It is free degree of freedoms. This is free. This point can go up and down, left and right, and it can rotate as well. So it is free. This point here can, point C can have free left to right, go up and down free, and it can rotate as well. So that is free. I hope it makes sense. This is free. This is free, and this is free. This point here is fixed, so this is fixed support, so it is fixed. Fix here. Fix here. Again, this point is fixed, fixed, and fixed. So how many fixed? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is fixed. And out of another 9 is free. Right. So I hope you understand that. 9 plus 9 is 18. So that is 18 degree of freedoms. And out of 9 and this one. So the numbering that we're going to do it will depend on these ones. So I think the if I remember that one, so let me think. So fixed degree of freedom, free degree of freedom goes with so the lowest number goes with the free degree of freedoms. So whenever you see free, so that is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So where is that? You can put 1, 2, and 3. There is no any issue which one you're going to put. You can put 1, 2 here, but the lowest numbers, when you see the free degree of freedoms, that will goes with the lowest degree of freedoms. Like if you need to rank them from 1 to 18. You need to start from 1 and finish at 18. Now you have a choice that who do you give the 1. Now the 1 that you want to give 1 to 9, because there are now again there are total 1 to 18. Out of 1 to 18, there are first 9 is a free. Sorry, the 9 is free, 9 is fixed. Now which one goes first? All the free degree of freedoms will goes first. So when you rank the degree of freedoms, you generally rank the free degree of freedom first. So that is 1, 2, 3. You can put 1, 2, 3 here. There is no any issue, but all 9 first 9 should goes with the free degree of freedoms. There is a reason for it. So there is 4, let's say 5 and 6, and 7, 8, and 9. And the remaining fixed one, you can put 10, 11, and 12, 13, 14, and 15, and 16, 17, and 18. Right. So that is the whole modeling. Little bit tricky, I think, but you know the story that you have done this kind of a work before, so you know the story for this kind of things. So unmute yourself if you have any questions on this one. So unmute yourself saying this part I did not understand, or I know it looked like a circus with the different name and different things and all, but I hope. So we have total 18 degree of freedoms. Total 18 degree of freedoms meaning you have day 6 and you have total 18 degree of freedoms. That's given here. Okay, just give me a minute. All right, so last part. The last part, I think you are seeing the screen. So the last parts, we have total 18 degree of freedoms. I hope you everyone understand that. Total 6 nodes. Each node has a 3 degree of freedom. 6 times 3 is 18. Now there are fixed supports when you have a fixed support. So let me give you the summary as well. So if you have a fixed support, let's say if you have a fixed support, if it is fixed, meaning that this point is completely fixed. This degree of freedom is fixed. This degree of freedom is fixed, and this degree of freedom fixed. When you have a pin, for example, let's say someone give you the pin, and for that pin, this degree of freedom fixed because this point cannot go left or right. This degree of freedom fixed, but this one is free. You can imagine that this point is like a door hinge. It's like this pen. This point is a pin. Let's say fixed degree of freedoms is tight holding, so it cannot go left or right, cannot go up and down, and it cannot rotate. So that is a fixed degree of freedoms. It does not have any rotation, any translation, any translation, longitudinal displacement or transverse. This is fixed. If it is pin, meaning like this, it can roll, and but this point cannot go left, right, or cannot go up and down. And there is a roller. If I have a roller here, then the point here with the rollers, this is again free because it can roll. This one is fixed, and this rotation is free as well. So I hope you understand that. Fixed meaning all three are fixed. All three are fixed. Pin meaning two are fixed. Which two are fixed? Those translations, this horizontal translations fixed, this one fixed, and rotations is free. So two fixed, one free. If you have roller, you have only one fix. You have only one fix and two are free. So I hope you understand that one. Right? So three fix here, which is fixed supports. Here, two fix, one going left or right, up and down, two fix, one free. The rotation is free. In here, this roller, it can have this one fix, another one is free. Let me show you that you will just get this one. So look at this one. This scenario here. Let me explain you that. Okay, you look at here that you can see that roller supports. How does roller supports work? You have seen the columns and you have seen the beam. So in the real situations, you will not see the rollers like actually the rollers. You need to make an engineering decision that this point here can go left and right. You can see. So when you come across with the designing of these columns and beam in these situations, you can imagine that this is a rollers. You can see because this point here, these guys can slide left and right. This point cannot go up and down. You can see it can have restrictions, and this point can rotate. If someone jump on it, this will rotate. So this is a roller supports. In the real situations, you might see this one. Now pin supports that I told you that this point is going to be this point that going to be not going to go left, right, and up and down. You can see, you can imagine this one. If you have this kind of a slot, and if you put the beam here, this point cannot go up and down or left or right, but this point can rotate. If I apply the load here, this can start rotating. So this one rotating. Now fixed supports something like this, completely made together. Then you might consider this one is a fix. So I hope it is helpful here. This how the rollers works. This is the rollers. How the pin works. This is kind of pin, and this is a fix. Freedoms for these fix and free and so on. So in here last parts, we have total 18 degree of freedoms. Now out of 18, we have to identify which one is free and which one is fixed, right? So as I already explained you that those fixed supports has a 3 fixed degree of freedom. So this one has a 3, this one has a 3, this one has, because this is fixed support. So total total 9 fixed degree of freedoms. And these 3 points which are free, there is no support. So there are another 9 free degree of freedoms. Now out of 9, I have an options to put first degree of freedoms, right? Because that is the lowest, the number 1, number 2, number 3, number 4, and up to number 9. Now those degree of freedoms, which is starting from 1 to 9, which is falls in the free degree of freedoms, that will goes with 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you see the free degree of freedoms, it has a low number of degree, lowest numbers. Lowest number meaning when you are assigning the number 1, 2, 3, 4, 5, 6, those assignments or those definition of the numbering 1, 2, 3, and so on goes to the free degree of freedoms. Once you finish the free degree of freedoms, then you will go the fixed degree of freedoms. 2, 3, so remaining is 10, 11, 12, 13, 14, and so on. So that's the free degree of. So when I take an example, hopefully you will get more clear. And again, you don't need to remember this or you don't need to do it in your assignments. We will give you these details in your assignments. Now let's say this one is a pin supports here. This one is a pin supports. This one is a pin supports. Now we can start with putting the numbering. Number 1 element, number 2 element, number 3 element. We can put the location vectors 1, 2, and 3 location vectors are there. We can also put the node numbering 1, 2, 3, and 4. Again, load numbering does not matter which numbers goes first. You can put it 1, 2, 3, 4. This one's again element numbering does not matter. You can put 1, 2, 3 arbitrarily. Now the questions comes here that each point has a degree of freedoms. It has 3 degree of freedoms. Here it has another 3 degree of freedoms. Another 3 degree of freedoms. Now you can tell me how many total degree of freedom, please. You can count them and tell me how many total degree of freedoms for this whole frame. How many total degree of freedoms? 12. Everyone okay? So 3 here, 3 and 3, 6, 9 and 12. So total 12 degree of freedoms. Total 12 degree of freedoms. Now out of 12, how many free degree of freedoms and how many fixed degree of freedoms? Free and how many fixed? You can think about it here. Student saying that 8 is free and 4 is fixed. Yep, so let's try to do it. So this point cannot go left or right, so this is fixed. This one is fixed. This one is free. So this one is free. This one is free. This one is free. This one is fixed. This one is fixed. This one is free. And fixed, free, free, and free. So total 4 fixed, that's correct, and 8 free, correct. Now I have to divide this group 1, 2, 3 up to 8. That is your free degree of freedom. You already told me that, right? You identify yourself. And then remaining group is starting from 9 to 12. That is the fixed degree of freedoms. You already told me that. Now I have an options to go 1, 2, 3. That's we need to put it at the fix. So you can put 1, 2, and 3 as a fix. Sorry, free. 4, 5, and 6 that are free. So 7 and 8. So 7 here and 8 here. So that is our free. So when you put all these 1 to 8 number, it goes with the free degree of freedom. Lowest numbers of the degree of freedoms, the rank of the degree of freedoms goes lowest with the free and remaining is 5. Now someone will ask, does it matters from within 1 to 8 which numbers will going to put first? No, that is not a matter. Within 1 to 8, it does not matter which one you're going to put 1. It does not matter which one you're going to put 2. It does not matter which one you're going to put 3 and so on. So there is no any issue on this 1, 2, 3, 4, 5, 6 and so on. So there is no any issue for that one. For fixed remaining 9 to 12, there is no any issue that which one goes 9, which one goes 10, and which one goes 11, which one goes 12. So I hope it is makes sense. Any questions in putting those degree of freedoms? Now, probably I will not gonna go too much in the great details how this one going to work because it will be really complex and we will not going to ask you how this is gonna work. But we will have these transformations between the local and global systems. So let's say for the frame structures, the transformation between the local and global system is required since the frame is oriented in different directions. So what does it happen? You can see that you can see I can quickly explain you what is the global and local. So when you have this whole frame, that you are seeing on the screen, which I'm going to erase it right now. In that frame, you can see that this frame has a one global system. So these points here is a global system. So let's say represented by X and Y. So global system is kind of a representation of the whole systems where you have a 0, 0 here, like a starting point for this one. And then you can put some this Y, let's say 0 and 4 meters. Let's say this is 4 meter high. Let's say from here 2 meters. So you can have this another 1 meter up. So I'm just making it up. So you can have those coordinates. So this is 0, 0 and all, and you can have a coordinate. So this is your global systems. Now for local systems, each member has its own systems. For example, this one has a local systems and that's represented by X dash and Y dash. So each element has its own local systems. You can imagine this is X dash and Y dash. You can imagine this is X dash, this is Y dash. You can imagine this is Y dash and this is X dash. So each element has its own local systems, and when you join them together, it will have whole global systems. So you have a local systems and you have a global systems as well. So that's pretty much whole global and local work. So we need some kind of a relationship between the local and globals. Like we might have this theta relationship because the orientations, because you can look at this is X and Y, but these are at some angles. And for that angles, what is their relationship with the theta that goes with this one? So there is a rotations, which is theta, the angle that makes the relationship between the global and local. So that pretty much they're talking about here, that you have theta X and theta Y that representing the local to global. So we need to have some kind of a matrix that will develop the relationship between the global and locals. Let me close this guys here. Okay. All right. So far so good. Okay, so that's what I'm talking about. When you have when you want to transport the displacement from global to locals, I think there is a systems which I'm not going to go in the great details for this ones. I will give you the one straight away straight away those metrics. But basically, I'm going to explain you that D1 that is representing your translations, that is your local displacements. Like local displacement meaning you can see these points can locally go this way, like it can squeeze like this. So when you want to find this local displacement D1 dash, it has a relationship between this global D1, global D2, and it has a theta X and theta Y relationship. You can see theta X and theta X and theta Y. right? So that's what this is a local, and this is global. Again, d2 dash, which is these points going this way. When you go this way, again you have this global relationship, which is again theta x, and it's just a trigonometry, and this is a global d1 and d2. So that's rotations. The rotation does not matter. So you can see whatever rotate here, that will rotate in the local and global, same thing. That is not much difference. So whatever the rotation happens in the local systems, it will be same in the global system. And same philosophy which you done in this particular node, that will occur here. So limitations with d4, d5, and d6, which is d1. You can write it in the matrix form. d1, d2, d3. This is local. This is lambda x. By the way, we put lambda x instead of cos theta x. So somebody said, why, what happens to this 0, 0? Because you have this x, y, and rotations here. So there is x, y, and there is no rotation. So that is 0. And for this is a near node. So this is near node. And for this one, far node. So this is far node. There is nothing on here. So that is 0 for the far nodes. So here there is no anything. Again, this one is minus, this one is this one. There is no rotation, and again there is near node. So we are talking about these nodes. So this particular thing is this one, and far node there is nothing, 0. This one is rotation here. You can see 1. So 0, 0, 1. That is rotations. There is nothing about this ones. There is no near node. So this is we working on here. So there is nothing 0, 0, 0 at near node. But this one is all about x, y, and rotation 0, x, y, and rotation 0, and there is a rotation here. That's, you can see d1, d2, local transformations, and this is globals. This is force. The another one is a displacements. We can do the force transformation as well. Exactly the same. You have a global force, and you can transfer it into the local force. You have global force. So this is local. Let's say global force here in this directions. Another global force in this direction, which is Q2. Then you will get this relationship. Rotations, which is the moment. This is axial force, by the way. This is axial force, this is shear force, and this is moment at this particular node. So you have moments, and you transfer it into locals. Similarly, at these nodes, you can go to Q4 axial load, global axial force, and then you match it with you convert it into the local systems. Again, global Q5, which is shear, and you going to match it with the local. And this one is Q6, which is the global force, which is the moment, sorry, and that's match with D6, Q6. I think that is not D6, I think Q6 here, Q6 dash. Just make it correction here, Q6 dash and Q6 dash. So this is all that philosophy here, all these ones, and you have this relationship, which is local transform into globals. So stiffness matrix, again, you can do it one by one, and you superpositions. You know the truss elements. You remember that truss elements, and if you go back to our lecture notes, we will get this matrix for the truss elements like EA on L, axial stiffness on length, axial stiffness on length, and so on. So that's we already done for the truss. For the beam, we also developed this ones. If you look at the week number 4 and 5, we have developed this one. So nothing new for you. It's just written in the different format. And if you add them together, if you just plus them here, you get EA on L here, 0, 0. You get 12 EI on L cubed. You get all these details there. Now, I think nothing new for you. That is the force deformation relationship. Local force, local stiffness, local displacement, like force is equal to stiffness times displacements. That's the relationship that we just talking about, and that is all locals. Local to globals, local displacement, transformation matrix, and global displacement. We done it this one before here. So that's what local transformations did. Then if you have a global, you have a global force, free transforms, and local force. Now, if you take this relationship here, if you take this relationship Q, T transform Q dash, that you're going to get it K dash D dash. So T transform Q dash. If you have D dash, you can put T TD. And you do this, you can get KD. So you have all these big element stiffness for the global matrix that is here. If you put all these ones, you will get this big chunk of equations here. You can see that very huge big equations. Or if you don't understand any of these before these transformations, don't worry, we will not going to ask you. What we're going to do it, we're going to use these equations. You need these ones in your cheat sheet or somewhere that you can use these equations loud and clear. And I will show you how to use that equations in a minute. I will show you this one how to use it as well. All right. Again, let me explain you this ones. I think this is the same story. Let's we can come back to on this ones when I need it, because if I explain it, you will not understand. So that's pretty much it's all right. So let's get a 5 minutes. One notes to write on it. Week number 7 lectures, and let's get these details. As you can see, the modeling is given to us, so there is no any issue for us. So the modelings are here. Edit copy. Let's put it here. All right, so this is the one. Now, first of all, we like to get these equations, which is the peak stiffness. That's pretty much we like to use. Let me erase this one so this comes nice and clear. So we're going to get these big equations handy, and we're gonna get it here. All right, so this one we're gonna keep it in front of us. Let me move these ones a little bit on the side. Let's make it a little bit smaller so you can see. All right, so we have two elements. As you can see, we have element number 1, element number 2. It has a node numbering 1, 2, 3. It has total 6 degree of freedoms. We not worry about the fixed and free degree of freedom at the moment. Next week, we're going to look at the fixed and free degree of freedoms. So today we're going to get the stiffness matrix for the frame. OK, and we assemble them. Probably you can look at your assignment questions and you will find the similar things. So first of all, let's start with element number 1. Let's say element number 1. Element number 1. So for element number 1, our length of the element number 1, how do we identify where is the element number 1? The number with the square bracket represent element number 1. So this is element number 1. So you with me to say that this is my element number 1. If I put this one's here, element number 1, and you have an arrow location vectors, and the length of the element number 1 is 4 meters. You with me so far, right? Now, let me put this one on this side. So you are with me so far on that one. So that's all good. Element number 1. Stop me or put in the chat if you don't understand any of this one. Then we will have a degree of freedoms. Then we have a degree of freedoms. 7, 8, and 9. Right? Just copy that one, right? You can see this 7, 8, and 9. And here you have 1, 2, and 3. So far, so good. No questions, right? Unmute yourself if you have any questions regarding these ones. All right, let's say our global coordinate systems are sitting at here. This is our global coordinate systems, X and Y. So our 0, 0 would be here. So you with me that this coordinate would be 0, 0. and this coordinates here, that would be 4 meters. So 4, 0. There is no any y. So 4, 0. The coordinate for here, that would be 4, minus 4, because you have 4 meters. X is 4 and we are coming down, so minus 4. So here the coordinate is 4, 0. So lambda x. So this one is near node and this one is far node, because this is location vector is telling me this one. So if first we calculate lambda x, because you know we have lambda x and lambda y. So lambda x equal to this far node of x minus near node of x over length L. So we have far node of x is 4, which is here, minus near node of x is 0 over length is 4 meters. So that is lambda x equal to 1. Lambda y equal to far node of y minus far node of x over length L equal to 0 minus 0, because your far node of y is 0, far node near node of, sorry, this is near node. Near node of y 0 over 4. So it's 0 over 4 is 0. Right, so this is all good so far. So far so good. Now, so we have lambda x equal to 1, lambda y equal to 0. So whenever I see the lambda y, that I will put it 0. So this one is 0. This whole thing is 0. Lambda y is 0. Quite easy here. This one 0. This one whole thing 0. Lambda y is 0. So I hope you understand what I'm doing. This whole thing is 0. Lambda, sorry, this lambda y is 0. So this one is 0. Lambda x we have, this one whole thing 0, because lambda y is 0. Lambda y is 0. Lambda x we needed. Lambda y is 0. Lambda x we needed. There is nothing here. Lambda y is 0. Lambda x, this one, lambda y is 0. This one whole thing is 0. This lambda y equal to 0. This lambda y equal to 0. If we don't have 0, we can put it as values. OK, this one whole thing 0. This whole thing 0. So this whole thing 0. This one 0. This whole thing is 0. This is 0. This whole thing is 0. This whole thing is 0. OK, so that's pretty much 50% job is done. So we can calculate AE on L. Let's do that one. So let's calculate, because we need, you can see AE on L. So let's calculate AE on L equal to individually. OK. So AE on L, does it given in our questions? Oh yes, in our questions they have given the Young modulus and area and I. So let me get that details for you. In our examples, it has given these details. Copy, and we're gonna paste it here somewhere. Okay, so area is given to us. Okay, we gonna look at the units. The unit load is in the kilonewtons. So load is in the kilonewtons. Load is in kilonewtons and length is in meters, right? So length is in meters. So we have given area. Where is that? Oh, area is given 10,000. So we need to convert that area into meter square, because you can see length is in meter square. So area equal to 10,000 millimeters square equal to 10,000 over 1,000 times 1,000. So that will give you this meters. So meter square. So you have 0.01 meter square. So 0.01 meter square, that is area, times by Young modulus is given. Young modulus is equal to 200 gigapascals. In that case, we can say that 200 times 10 raised to power 9 pascals. Giga means 10 raised to power 9. So if I want to write that pascals, Newton, 1 pascal is 1 Newton per meter square. So meter square is fine. We just need to convert into kilonewtons, or we can keep it into the Newton per meter square. So let's keep it in the Newton per meter square, and we can just convert load into the newtons. 10 raised to power 9 Newton per meter square. Over length, we have 4 meters length. So if you use your calculators, you will get 500 times 10 raised to 6 Newton per meters. Okay, and AE on L done. What others we need? AE on L done. This one, oh, 6 EI on L squares. We need this, or 12 EI on L cube. We need 12 EI on L cube. You can see here 12 EI on L cube. So let's get that. Let's get that 12 EI on L cubed. So 12, I think E already we got it. So 200 times 10 to the power 9 Newton per meter square. That is your Young modulus. I, again, this is in the millimeter power 4. So let me get that sorted out. I equal to 3 times 10 raised to 8 millimeter to power 4. So if I want to convert into the meter power 4, 1000 one times, 1000 second times, 1000 third times, and 1000 four times. So if I convert that once, I would get 3. Let me use my calculator. 3 times 10 to the power 8 divided by. So you get 3 times 10 raised to minus 4 meter to the power 4. So meter is good because we're working in the meters. So I would be 3 times 10 to the power 4 meter to the power 4. That is I over L cubed is a 4 cubed. So the answer for that ones we will get 11. If I use the calculators, 11.25 times 10 to the power 6 Newton per meters. All right, so far so good. We are just finding those individual details. Now the next ones that we're going to get is this 6 EI on L square. So let's get that 6 here. I think most of the details are there, so we just need to use those details. L square. So here 6 E, we know 200 times 10 to the power 9 Newton per meter square. We got 3 times 10 to the power 4 meter to the power 4, that is the I, over length 4 square. So in that case, we might get 22.5 times 10 to the power 6 newtons. Now next one, we have this guys here, 4 EI on L. EI over L. So 4 Young modulus is 200 times 10 to the power 9 Newton per meter square. I 3 times 10 to the power of minus 4, by the way, here minus 4 meter to power 4 over 4. You get 60 times 10 to the power 6 Newton meters. And I think 2 EI on L, same thing, but just a half of that what we done. 2 EI on L equal to 2 times 200 times 10 to the power 4, 10 to the power 9 Newton per meter square times 3 times 10 raised to minus 4 meter to power 4 over 4. So we get 30 times 10 raised to 6 Newton meters. So these all the details which we have, we calculated. Unmute your back here. I hope everyone know where to get this matrix. These metrics are given in our lecture notes. All right, so that is all good so far. Now, by using this matrix, I will tell small k1, which is the stiffness for the element number 1. And I'm going to put this big brackets here for you. I'm going to put that big brackets here. And then I will continue. Now, the first one, A on L lambda x. Lambda x is 1. As you can see, where is it? Lambda x equal to 1. So 1 square is 1. And we have calculated this one is 0. This one is 0. We have calculated AE on L. So AE on L we got here 500 times 10 to the power 6. So let me erase these ones. 10 to power 6 times by 10 to power 6. Okay, you can go here. 10 to power 6. And you can see this one is 500 times 10 to power 6. So we have 500 here. Everyone understand that, right? 500. I put substitute AE on L. 500 times 10 to the power 6. This one 0. This whole thing is 0 because this one is whole thing is 0. This whole thing is 0. Let me erase this 4. Okay, so that 4 goes here. So this whole thing is 0. So we put this whole thing is 0. I'm just putting exactly on the down. This one, these things are 0. AE on L, which is 500. And we have this minus in front of it. So minus 500. I hope you understand that. AE on L 500 times 10 to 6. This minus we put it here. Lambda x is 1. So 1 square. Minus this whole thing is 0 because we have lambda y is 0. So the whole thing is 0. So we have 0 here. And this one's 6 EI on L squared. So and this is lambda y. So this whole thing is 0. So I hope it is clear for you right now to get this first 6 numbers on the first row. Second one, this whole thing is 0. So the whole thing is 0. These things are 0, but you have 12 EI on L cubed and lambda x square is 1 square. So 12 EI on L cubed, we got 11.25. So 11.25 times 10 raised to 6. And I put the common 10 raised to power 6 on here outside. So that's 11.25 times 10 to the power 6. Lambda x, this one's 6 EI on L square. 6 EI on L square is 22.5. So 22.5 times 10 raised to minus 6 outside. So we have put this second one. This whole thing is 0. So the whole thing is 0. This one here. This one, we have negative sign here. So we put negative. And 12 EI on L cubed. 12 EI on L cubed is 11.25. So 11.25 and 10 raised to minus 6, we take it common. This one 6 EI on L square. 6 EI on L square is 22.5 and is positive. So 22.5. So I hope you know how to get this second row as well. Third row, this one is 0. This one is 0. lambda x 6 EI on L square. So that is 22.5. 4 EI on L, which is 60 times 10 raised to minus 6. This one 0, this one 0. Minus 6 EI on L square, minus 22.5. 2 EI on L, that is 30. I hope you understand that. These things are 0. EI on lambda x squares minus 500. Minus EA on L, which is 0 here, that is 0 here. 6 EI on L square lambda y is 0, so that is 0. Lambda y is 0, EA on L lambda x square, which is 500. This whole thing 0, 0. Whole thing 0, there is 0. This whole thing 0, 0. This one 0, we have minus sign outside, so minus 12 EI on L cubed, 11.25. 6 EI, this one we have minus 11.25, so we have 22.5. This one 0, this one 0. Lambda, this one 0, lambda x 12 EI on L cubed, 11.25. This one minus 22.5. This one 0. Whole thing is 0. 6 EI on L square, 22.5. 2 EI on L, 30. Lambda y, 0. This one 0. Lambda x minus 22.5. And 4 EI on L, 60. All right, so that is all good so far. So that is the element number 1. Now the numbering. So first 3 columns goes with the near node. You can come back here. That is the near node. You have 7, 8, and 9. So you put x, y, and rotations. X, 7, 8, and 9 for near node. And then you put far node 1, 2, and 3. And you put far node 1, 2, and 3. And similarly 7, 8, and 9, and 1, 2, and 3. Right? I hope you understand these stories. Now, same story. I will be a little bit faster, but we will do the element number 2 here. Element number 2. I will be a little bit faster because you know the story now. So element number 2. Element number 2. Length is 4 meters again. And if I draw the element number 2 here, if I can get this one here, then we can see it. Yep, there you go. You can see it. Element number 2. It has 4, 5, and 6. It has 4, 5, and 6. Location vector going this way. And you have 1, 2, and 3. And if you know that coordinates 4, 0, 4, minus 4. 4, 0, and 4, minus 4. Now lambda x, so this is near node. And this one is far node. Right, so lambda x, we will do it. This is near node x, near node y. Far node x, far node y. So x meaning far node x minus far node y over length. So far node x is 4, Far node y is 4, length is 4, that is 0. Lambda y, sorry, near node, far node x minus near node x, sorry. This one, near node x. Far node y minus near node y over length. So far node y is minus 4, minus 0 on 4 equal to minus 1. Now the same story, you remember that element we got it, AE on L, 12 EI on L cubed, 6 EI on L squared, 4 EI on L, 2 EI on L. We're going to do the same thing. But I'm not going to show you again all these ones. Area, you know, Young modulus is same, length almost same. So AE on L, same thing. 500 times 10 raised to minus 6, nothing much difference, okay? Because it has same area, same Young modulus, same length. You can look at this one here. If you want, you can repeat these ones here. These ones, how I get it. Second, 12 EI on L cubed. 12 EI on L cubed. Same thing, like the element number 1. We have 11.25 times 10 raised to 6 Newton per meters. Six EI on L square. Same thing, 22.5 times 10 raised to 6. I hope you know what I'm doing. 4 EI on L, which gives me 60 times 10 raised to 6 Newton meters. 2 EI on L, we got 30 times 10 raised to 6 Newton meters. So now we can use the same. We can use the same equations because the length has not changed. So therefore we got the same. Luckily, we got the same values. If the length is changing, we might do it differently. So now we have K2 equal to 10 raised to power 6 again outside, and we can just draw it up. Now in here, lambda y is minus 1 and lambda x is 0. So we put this one 0 and 12 EI on L cubed, which is 11.25. This one lambda x is 0, so that is 0. Lambda y is 0. Lambda y is minus 1, so we make it positive. So 22.5 positive because this is minus 1, so minus minus positive 6 EI is 21. Lambda x is 0 and this is minus. Oh, by the way, I forget to tell you one thing. You can look at these ones. This row is same. These numbers are same. These numbers, sorry, which one? These numbers are same. These numbers are same, matching, and all these diagonals are positives. So you can imagine these verifications within. All right, so that's all good so far. And I'm just going to put those details here. I think you know where all these details coming. 0, 22.5, 0. We have 500. We have 0, 0. We have minus 500. We have 0. We have 22.5. We have 0. We have 60. We have minus 22.5. We have 0. we have 30 minus 11.25, 0 minus 22.5, 0, 0, 0. 11.25, 0 minus 22.5, 0 minus 500, 0, 0, 500 and 0. 22.5, 0, 30 minus 22.5, 0, 60. All right, so now we can do the near node, far node business. Here you can see this is near node and 1, 2, and 3. So you have 1, 2, and 3, X, Y, and rotation. You have 4, 5, and 6. You have 4, 5, and 6. 1, 2, and 3, 4, 4, 5, and 6. Again, you can verify yourself. These numbers are same as these numbers. These numbers same as these numbers. These numbers same as these ones. These numbers same. This number same. Diagonal all positive. Right? So that is the verification for you that you can look at whether those numbers are matching or not. Now we can assemble them. Capital K is equal to K1 plus K2. I will show you one or two and then we can do it and then you can do it yourself. So capital K, how many total degree of freedoms we get? We get total 9 degree of freedoms. You can see total 9 degree of freedoms given here, total 9 degree of freedoms. So we will get 9 by 9 matrix. So 10 to the power 6, first we can put it outside. And we will get 9 by 9 matrix. So let's put it later. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And here. And similarly here. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right. So 1, 1. So you have 11.25, 1, 1. Here you have 500, 1, 1. So 500 plus 11.25, you get 511.25. Column 2, row 1. Column 2, row 1, 0. Column 2, row 1, 0. So you get 0. Column 3, row 1. Column 3, row 1, 22.5. Column 3, row 1, 0. So 22.5. You understand that? And number 4, row 1 minus 11.25. There is nothing here, so just minus 11.25. Column 5, row 1. Column 5, row 1, 0. There is nothing on these ones here. There is nothing, no 5. So that is good. Number 6, column 6, row 1 is 22.5. So now you can fill all these cells. But my job now to show you the Excels because last 15 minutes I want to show you the Excel. So I hope you can fill the whole one by yourself. So now the last parts, because this is a lot of manual work, we generally like to use the Excels in all our so elements. We have element 1, element 2. We have a area of the element 1, and that is in meter square. we can just copy that once. I think from here we got area somewhere. We calculated area. Here you go, 0.01. If it is different area, we can put different and 0.01. So that area is done. Young modulus in Newton per meter. Newton per meter squares, and we also got the Young modulus 200 times 10 to the power 9. 200 equal to 200 power 10 to 9. And you can just scroll it down. Moment of inertia, meter to the power 4. Okay. That's we got something 3 times 10 to the minus power 4 equal to 3 times 10 to the power minus 4. So that's you got I. Now AEL length in meter. I think both get 4 meters and 4 meters. So that's all good so far. Now we need few things. I think you know what we need. We need 12 EI on L cubed. Oh, we need lambda x, by the way. So lambda x for element 1 is 1 and 0. So lambda x is 1. And we need the lambda y. Lambda y was 0. In here there was 0 and here was minus 1 if I remember. And then we need something called AE on L. So we will get AE on L equal to area times E divided by length. So that's good. And we get same thing for here. Second, we need 12 EI on L cubed. We need 12 EI on L cubed. So 12 times E times I divided by L cubed. So you have 12 EI on L cubed. I think next one is 6 EI on L square. So 6 EI, a little bit faster, by the way. We done this kind of exercise. You can do it in your own time. 6 EI divided by L square. So 6 EI L square. 4 EI on L and 2 EI on L. 4 EI on L and 2 EI on L. So 2 times E times I divided by length. We can just have the same thing, but we will have 4 here. And we just scroll it down. So to get this one here and this one here. This one looks good. Now we can get this guy, big guy here. Let me close it off a little bit more. Here you go. So we will have element number 1. Let's put some coloring. Let me put element 1 and K1. So for K1, we would have these ones here. We need the 6 by 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6. So that is 6 by 6 matrix. That is here. Now in here, you remember that one we done already. 7, 8, 9, 1, 2, 3. So we can put 7, 8, 9, 1, 2, 3. Right. So you know where this coming from, right? We done it this one. So 7, 8, 9, 1, 2, 3. So 7, 8, 9, 1, 2, 3, and we got this. Now first one equal to bracket EA on L. For completeness, I will do everything. OK, so when we change the numbers, we don't need to worry about. So AE on L times lambda x squared plus 12 EI on L cubed plus 12 EI on L cubed times lambda y squared. What happens here? Oh, bracket over. OK, that's I just closed the brackets. I did not close the bracket, so they did not like it, but they close it. OK, so that's all good. And 500 times 10 raised to minus 6. You can check it. The first one that looks amazing. Good. Number 8 bracket AE on L minus 12 EI on L cubed minus 12 EI on cube times by lambda x times, sorry, what happens here? Times lambda x times lambda y. Whoa. OK, so 0, perfect. Let me put everything in the middle. Number 9 minus equal to 6 EI on L square, 6 EI on L square times lambda y. OK, all good. Number 1 here equal to minus bracket AE on L, AE on L times lambda x square plus 12 EI on L cubed minus lambda y square. Sorry, that is a little bit boring for you, but I can't make it. Where are we here? I can't make it more entertainment than this one. So minus 500. Let me put these details on my other screen so I know that you are doing correctly. OK, number 2 equal to minus. I'm just typing it up here. Minus AE on L minus 12 EI on L cubed times by lambda x times by lambda y. So you get 0. Number 3 equal to minus 6 EI on L square times lambda y. 0. OK, so that's all sounds good. I think this one is exactly the same, so we can copy. Control C, because there are too many. Control V, so that is 0. This one here, which one is same? This one here, so 6 EI on L squared. So this one's exactly the same. So Control C, and we put Control V. We put. I think this is a little bit faster. I think you will like these ones. We just copy because you know that this row is just the copy and Control V. OK, so that's perfectly fine. So now we are here. AE on L lambda y square. So equal to bracket AE on L lambda y square plus 12 EI on L cubed plus 12 EI on L cubed times lambda x square 11.25. 6 EI on L square lambda 6 EI on L square times lambda x back. All right, minus bracket AE on L minus 12 EI on L cubed times by lambda x times by lambda y. 0 equal to minus bracket AE on L times, I'm just working on here, lambda y square plus 12 EI on L cubed times lambda x square. It's all good. And 6 EI on L square. 6 EI on L square times lambda x. All right, so same thing here. We can copy this guy onto here. So we are filling it up a little bit faster. These guys need to be goes here. These guys will be here. And these guys be here. So that's all good. We fix up all this. We are in the third row. This one 4 EI on L. Third row, yeah, 4 EI on L equal to 4 EI on L. Sorry. 4 EI on L. For EI on L is something wrong. 4. Wrong one. 4 E I. Yeah, make sure you done some corrections here. You can see when I done something happens in between. So 4 EI on L, that is better. And 2 EI on L, that is better. Okay. That sounds a little bit better. So where are we here? 4 EI on L. So that is all good. 6 EI on L square. So we are here 6 EI on L square. 6 EI on L square times by lambda y. I think we may not be able to finish all, but that's okay. We can come back next week and do it. And we have 2 EI on L. We have 2 EI on L. So this is all good so far. So we can copy. Oh. Something I screwed up, or row 3. Row 3. That is row number 4. We need to work on here. So what happens here? Let me check. 500 0 0 minus 500 0 0 11.5 22.5 0 minus 11.2 22.5 0 22.5 60 0. Okay, this one something wrong here. So let me check again. 1 2 3. There you go. You need to put this one in here. 6 EI on L square lambda. Okay, I found it. 6 EI on L square times lambda y. Times lambda y. That is better. And minus 6 EI on L square times by lambda x. Yep, that is better going. Equal to 2 EI on L. That is better. So here we can just copy this one here. Control V. We just copy this one. Control C. Control V. Control C. Control V here. All right, so that looks good. Now we are 1, 2, and 3, and 4. So AE on L. I think we just need to leave it and come back to it. Lambda x square. Next week we're gonna continue from here. Okay, this is last one. I'm going to do it. 12 EI on L cubed. 12 EI on L cubed times by lambda y square. Yeah, in your own time you can finish it off, but from next week I will show you all these 4 5 in first 5-10 minutes, and then we will